Welcome to class today. And today's topic is going to be space stuff. And so let's get some basic definitions of like rocks out in space. So we have what's called a bolide. And a bolide, to a geologist, is space rock of unknown composition. So it might be an asteroid, it might be a comet, it's just some sort of miscellaneous space rock. Now, if you study astronomy, that definition is going to be a little bit different, because to an astronomer, a bolide is an object that makes an explosive amount of light as it enters the atmosphere. But this is geology class, so I'm giving you the geology definition. All right, so what are some of these bolides, some of these spaced objects out there? Well, you could have asteroids, and asteroids was like one of my favorite games when I was a kid. And you'd like have a joystick and you'd be like pew pew and shooting these asteroids and stuff, and apparently I probably just dated myself to the 1980s. But anyway, other than like my favorite Atari game, asteroids are pieces of space rock orbiting the sun. And many of them are in an area called the asteroid belt that is between Mars and Jupiter. A whole bunch of them orbiting out there. So this is a basic diagram of our solar system, but this is not to scale. And you can see here's the inner planets, Mercury, Venus, Earth, and Mars. There's that asteroid belt, and then we get to the outer planets. All right, but there are other objects, you know, that are out there. There's these things, these Kuiper belt objects and other stuff out in space. And some of those are comets. And a comet is a mix of ice and rock that orbits the sun. And maybe you were lucky enough this summer, there was a comet that came close called Neowise. And for a little while in July, you could actually, if you were at a remote enough place where there wasn't a whole lot of light pollution, you could see Neowise in the sky. And anyway, these comets, when you see them, and if they get close enough, there's the head of the comet, and then there's going to be this tail coming off it. And there's two basic places where your comets come from. You have what are called your short period comets that orbit the sun within 200 years, and they come from the Kuiper belt. So a comet like Halley's Comet that returns every, gosh, I don't remember how many years, 76 years, I think. Anyway, that's a short period comet because it returns within 200 years. Neowise, that was around this summer, is a long period comet because it's only going to return in several thousand years. So these short period comets come from the Kuiper belt, but those long period comets orbit the sun, like I said, greater than 200 years, and they come from an area way out there in space called the Oort cloud. So if we were to look at this, here's our basic view of the solar system. There's the sun and the planets orbiting it. The Kuiper belt's right out here, kind of beyond the farthest of the planet. But then that is this, right? Way out there, there's the Oort cloud. And that's why it takes so long for these long period comets to come in and go back, because it's such a long distance. So it can be thousands of years before these comets actually come back around the sun. All right, so those are the asteroids and the comets. Now, what about a meteor and a meteorite? Well, a meteor is an object that produces light in the sky as it enters Earth's atmosphere. Basically, as it starts traveling through Earth's atmosphere, there's friction, which causes it to glow. Like this, right? We have this meteor streaking through the sky right there. Well, what's the difference between a meteor and a meteorite? Well, a meteorite actually survives travel through the atmosphere. See, most meteors are so small, they completely vaporize, they completely burn up in the atmosphere. But a meteorite is big enough that it survives traveling through the atmosphere and it actually lands on Earth. And most people think meteorites look like this, but, well, some do, but definitely not all of them. So, what about this meteor and meteorite as it's going through the atmosphere? What does it experience? Well, these things begin to glow about 70 miles high as they enter the atmosphere. And they glow enough and become visible to us here on Earth's surface, usually by the time they're about 60 miles above us. Most of them, though, are gone by about 35 miles high. And so they just completely burn up. These things are traveling ridiculously fast. They enter the atmosphere traveling around 11 to 72 kilometers per second. You can see there's like 25,000 to 160,000 miles per hour. So these things are really, really traveling. Now, most of the meteors you see in the sky that people would call shooting stars, right? Those flashes of light that streak across the sky, most are tiny. Most are only about the size of a grain of sand. And that's why they vaporize as they travel through the atmosphere. You need to be bigger in order to actually reach Earth's surface. So if these things reach Earth's surface and become a meteorite, I said some of them look like that piece I showed you, but not all. Well, that's because there are different compositions of meteorites that exist. The one that most people think of with meteorites are these iron meteorites. But they're actually not the most abundant, only about 6% of all meteorites. And these are composed of a nickel-iron alloy, so it's very metallic. That's why these things tend to be really heavy when you pick them up. And if you cut one of these open, on the inside you're going to see Widmanstätten lines. So that's what the outside of one of these meteorites, these nickel-iron or iron-nickel ones, looks like. If you cut one open, that's the Widmanstätten lines, this weird pattern. And what that is, that's intergrowths of these rare nickel and iron alloys. Alright, but that's only one type of meteorite that we get. We also have stony iron meteorites. These are quite rare, and what you have are iron magnesium silicate minerals in a nickel-iron matrix. That means you're going to have like little crystals of minerals like olivine and pyroxene. Those minerals are these iron magnesium silicates. They're usually kind of a greenish color. They're going to be surrounded by that metal, just like what we see here. Here's those iron magnesium silicates, and this is the metal surrounding them. But there are other meteorites that are more common, more abundant, and these are the chondrites. Chondrites are the majority of the meteorites that we see. And what you're going to have is you're going to have little balls, little blobs of nickel iron surrounded by iron magnesium silicate minerals. So it's kind of the opposite of this previous one, right? In the stony iron, it was the minerals surrounded by the metal. In this case, it's these little bits of metal surrounded by the iron magnesium silicates and also feldspars. Now, the additional thing that you'll have in chondrites are these little spheres called chondrules. Now, I do want to point out that there is a special type of meteorite called an achondrite that does not have these little spherical chondrules in it. And that you do get these sometimes. So this one is a chondrite where we have these nice little blobs of iron-nickel alloy surrounded by your silicate minerals. And we also have these nice little spherical chondrules in there. But you can have achondrites, where we don't have those nice little spherical chondrules in them. And these basically just look like a chunk of the volcanic rock basalt. So those are some of the different types of meteorites that we have on Earth. And they do strike Earth. Just some years ago, there was a meteorite impact in Russia that made the news. But when we look at Earth versus the moon, you're going to notice that on the surface of the moon, there are a whole heck of a lot of craters from meteorites impacting there. But then you look around on Earth and there's definitely not that many. I mean, there are some. You could go visit a place in Arizona or a couple places in Australia or Canada or Africa, South Africa. But definitely Earth's surface isn't dotted with craters everywhere. So that should get you guys thinking, why is that? Why does the moon have so many craters and Earth doesn't? And normally I'd ask you in class, give me some of your hypotheses. Well, I can't really do that via this. So I'll imagine that you guys are all just such incredible students, and you would have answered. Actually, you are all incredible students, right? So every one of you would have said, what about plate tectonics? Right? Plate tectonics is always reshaping Earth's surface, building up mountains in places. And then it's also, because mountains get built up in some places, you have weathering and erosion that wears stuff away. And so we can be like wearing away ancient meteorite craters, and then the sediments can actually bury those ancient meteorite craters. So we just don't see them on Earth like we do on a place like the moon, where there's no plate tectonics and no weathering and erosion. But if we do look at Earth, we can see that there are meteorite impacts. All of these little dots show where there are known impact craters. You'll see that there's even one here in Texas, not far from where we are. And you're like, well, why can't we go visit it? And again, this is one of those that is ancient and buried under much younger sediment. But there you have it. We do have meteorite craters on Earth. Now, when meteorites strike the planet, they are going to create a crater, and depending on exactly how big the meteorite that hits is, what angle it hits at, what velocity it hits at, it can create different shaped craters. But we're just going to simplify this and look at the two most basic type of meteor craters that you can get. The first one's going to be a simple crater, and it will be bowl-shaped. And these form from smaller meteorites. If we take a look at what happens, we have our meteorite hit, shock waves go through the rock, we get our initial excavation of the crater. Now that's gonna blast out debris from the crater and probably the meteorite, and this stuff's called ejecta. So we're going to, after this meteorite hits, we're going to get this simple bowl-shaped crater. We're going to get all the stuff that got blasted out. This ejecta is going to cover the area around there. The rock around the crater is going to get fractured, right? Because this was quite a strong force hitting the rock. You're going to get all these cracks developing in there. You might even get some melt. Right? So there's a lot of heat involved with this meteorite hitting, so some of the material can melt. And you're going to end up then with this bowl-shaped crater with some impact melt, some of this ejecta. And one thing to pay attention to, the edges of that crater actually bulge upward. So as you approach the crater, you'll actually go kind of uphill before dropping into the crater. Now that's a simple crater. Of course, that's from, like I said, the smaller meteorites. Well, what happens if you have a larger meteorite hit? Well, then you get a complex crater developing. And these are going to be quite wide compared to their depth. So they're going to be really wide and shallow. They have a central uplift. So they got forced down with such force, the rocks kind of bounce back up in this central uplift. And these come from the much bigger meteorites. Again, you're going to have this initial excavation with a shock wave, but you have, like I said, this rebound of the material that got pushed down. Now you're also still going to have some of the material will melt, and some of it will get blasted out of the crater as this ejecta. So ultimately your final crater, see how it's quite wide compared to how deep it is? You have the central uplift and you have this ejecta around it. And this slide right here simply summarizes the difference between our simple crater and our complex one. The diameter of the complex one is much greater, though the depth appears less, and this is that nice simple bowl shape that we get. All right, so let's get an example of a simple crater. We're going to travel to the Barringer crater in Arizona, what people commonly call Meteor crater. And you see as we drive along this road, there's this hill in the distance. That's that rim that I said got bent upwards a little bit. So we drive up there and then eventually we get to see this crater. This is very young. This was from a meteorite impact about 50,000 years ago. It's about a mile across, and the meteorite that hit there was something like 25 to 40 meters in diameter, something like that, give or take. And that's the crater that resulted from that. Now this is the Manicouagan crater in Quebec in Canada. This is actually a satellite image, and you can see we're almost 100 miles above Earth's surface where this imagery was taken. And central uplift is now Manicouagan Island. You can kind of see the edges of the crater right there. This is not as nicely preserved as Meteor crater because this is much older, hundreds of millions of years older, and glaciers scraped across that area. So this is kind of all we have left of this much larger complex impact crater. All right, so those are some of the craters, but like I said, no matter, those are the simplified ones. Depending on exactly the angle the meteorite hits at and the velocity and what type of meteorite it is, you can get some little differences in the craters developing. So the next thing I want to take a look at is how do we know when meteorites have hit Earth? Because I'll give you an example of this. In the early 80s, it was still a mystery of how the dinosaurs died out. And the Alvarezes, two scientists, a father-son team who worked together, hypothesized that a meteorite had hit Earth at that time to kill off the dinosaurs. Well, what kind of evidence would they have looked for to see that a meteorite hit? And what kind of evidence could other scientists look for other meteorite impacts? Well, obviously, there's the crater, right? If you find a crater, maybe it's a meteorite. Now, granted, craters can form from other things as well, but that's a pretty obvious one. Well, there's the ejecta blanket. There's all that stuff that got blasted out of the crater and covered the area around there. There's the impact melt, right? I told you in both of those meteorite impacts, there's a lot of heat involved, whether it's a simple or a complex crater. Doesn't matter, lots of heat, you're going to get some melting. And this is going to be both the meteorite and the target rocks. The rocks that got hit will melt. And oftentimes this is going to be enriched in nickel, iridium, and platinum, as well as some other metals. And these are metals that, yes, we have them on Earth, but not in huge abundances on Earth. They're in much greater abundance out in the solar system. And so when you find these minerals in abundance, there's a good clue that maybe there was a meteorite impact. You can also find what are called tektites. Tektites are where some of the molten material, right, some of this melted material flew through the air, and as it was flying through the air, it cooled. And cooled into what looks like obsidian, right, because it is glass. And, but it also, these usually cool in aerodynamic shapes because they're cooling as they fly through the atmosphere. Other things that can show us that a meteorite impact has happened is shocked quartz. Shocked quartz, now you can only see this under a microscope. So this isn't something where I could pick up a rock and be like, aha, shocked quartz. You have to look at the rock under a microscope. And normally, quartz under a microscope looks like this. Each one of these is a little sand grain of quartz. Shocked quartz looks like this. See those lines in there? Those lines are where the force of the meteorite impact actually disrupted the crystal structure of the quartz and created those lines that we see. And when you see that, you know that a meteorite impact has happened because other things do not have enough force to create that.